Hello, everyone, and thank you for joining our session about deploying HPC and AI on Google Cloud with NVIDIA GPUs and the Hypercompute Cluster. My name is Wyatt Gorman. I'm one of the product managers for high performance computing at Google Cloud. And today I have with me Sam Skillman, one of our software engineers focused on HPC and AI, as well as Mahir Pandya, a technical staff member at Contextual AI. During this session, we'd like to discuss Google's HPC and AI infrastructure and our newest addition to our infrastructure, the Hypercompute Cluster. We'll then share a bit more about our Cluster Toolkit and some of the blueprint examples available for the toolkit before handing it over to Contextual AI for them to share how they're using Google Cloud to run their ML workloads. Let's start with the foundations of today's talk by covering the fundamentals of Google Cloud's HPC and AI infrastructure. Let's start by taking a look at our HPC roadmap. This will give you a good view of the investments we've made across our HPC infrastructure ecosystem over the last few years, whether that's core infrastructure components on the top, platform and service capabilities below that, or partner solutions and success stories on the bottom. In infrastructure, you can see the progress we've made over the last few years in introducing the latest and greatest NVIDIA GPU types to our portfolio, including L4s, H100s, H200s, and more. In services and software, you can see the work we've done to build our own tools and manage services to simplify running HPC in Google Cloud. And in partner solutions, you can see the investments we've made along with our partners to drive support and optimizations in Google Cloud for their job schedulers, storage systems, end user applications, and so on. All of these investments have culminated over the years into a single comprehensive HPC platform that is optimized and purpose-built for HPC and AI workloads. That platform consists of three key tiers: performance-optimized infrastructure, open software, and flexible consumption models. Let's talk a little bit more about our infrastructure before we move on to our open source software and flexible consumption patterns that are encapsulated within the Hypercompute cluster. Google offers a wide range of machine families to cater to both general purpose and specialized workloads. General purpose VMs are suitable for a variety of applications such as web serving, business intelligence applications, and back office use cases. Specialized VMs are purpose-built for workloads like HPC and AI, with compute-optimized CPU VM types and GPU-enabled accelerator-optimized VM types. For HPC and AI workloads, the A-series VMs are accelerator-optimized with a variety of GPU types available. These specialized workload VM types also benefit from a series of HPC optimizations and tunings that we'll discuss in the next section. Today we have the A3 VM family available on Google Cloud, including the H100 and H200 GPU platforms with up to 3.2 terabits per second of GPU-to-GPU networking and RDMA acceleration. Each A3 VM type is a unique shape that's optimal for different use cases. For example, the A3 Ultra might be optimal for high network I/O workloads versus the A3 High for single node or single GPU performance. We also announced Google Cloud's launch of the A4 VM at GTC this year, and A4 VMs are powered by B200 GPUs and offer 2.25 times the performance of an A3 High VM at peak. You can learn more about the A4 VMs on our website or in its dedicated GTC session. But as HPC and AI practitioners know, it's not just about individual accelerators or VMs. With AI and HPC workloads, you need to deploy, manage, and optimize very large numbers of AI accelerators and their associated networking and storage, which can be very complex and time-consuming. Over the last few years, we've seen the need for our infrastructure to change to meet the demands of high-performance computing and AI workloads. In response, we've developed a new product called the Hypercompute Cluster. The Hypercompute Cluster streamlines the infrastructure and workload provisioning and ongoing operations of HPC and AI supercomputers with up to tens of thousands of accelerators. At its core, Hypercompute Cluster combines the best of Google Cloud's AI infrastructure technologies so you can seamlessly deploy and manage a large number of accelerators in a single unit. With features like dense co-location of resources with ultra-low latency networking, targeted workload placement, and advanced maintenance controls to minimize workload disruptions, the Hypercompute Cluster is built to deliver exceptional performance and resilience so you can run your most demanding and largest scale AI and HPC workloads on Google Cloud with confidence. You can set up a Hypercompute cluster with a single API call from pre-configured and validated templates for reliable and repeatable deployments. This includes containerized software with frameworks and reference implementations like JAX, PyTorch, and MaxText, orchestration tools like Google Kubernetes Engine and Slurm, as well as popular open source models such as Gemma 2 and Llama 3. Each pre-configured template is accessible as part of the AI hypercomputer architecture, and it's validated for performance and efficiency so you can focus on innovating for your business. At the core of the AI hypercomputer is a new control plane that understands clusters the way that HPC and AI workloads do. That means that dense deployments, new consumption models with dynamic workload scheduler, enhanced maintenance controls, scheduling innovations, topology awareness and controls, and improved resiliency and fault tolerance for large-scale clusters come to fruition. Let's dive into the specifics of how a few of these features work. Key components of the Hypercompute cluster are the improved networking for HPC and AI workloads, including RDMA support and topology awareness. RDMA enables predictable, low latency, and consistent bandwidth between nodes, which improves the performance of collective operations, resulting in improved runtimes for workloads that can utilize it. In addition, IPUs offload networking overheads from CPUs, returning previously lost CPU cycles back to the user. Google Cloud's RDMA supports the native RDMA libraries that the community already uses out of the box, including GPU Direct RDMA, and it's included in the HPC VM image and accelerator-optimized OS images, which support Rocky Linux and Ubuntu. The topology API is used in the Hypercompute cluster to determine the configuration of VMs across the Google Cloud network and identify how VMs are placed in terms of blocks and subblocks in the Google network, which is analogous to director class and top-of-rack switches. Topology awareness ensures that communication happens as efficiently as possible between devices that are as close together on the network as possible in order to minimize latency and improve performance for tightly coupled workloads. Our automatic topology awareness comes pre-integrated with Slurm and Google Kubernetes Engine, allowing them to build and maintain a network topology for each individual job on the cluster. Improved consumption models and scheduling are another key component to the Hypercompute cluster. Google has long offered on-demand, spot, and committed use discount consumption of VM resources. However, we recently introduced the dynamic workload scheduler, which further unlocks HPC and AI-style resource scheduling. The dynamic workload scheduler introduces a consumption pattern between on-demand and committed use, where by sharing a bit of information about the resource requirements and the scheduling, Google can ensure better access to the resources as requested for our users. Dynamic workload scheduling comes with two modes, Flex Start mode and Calendar mode. With Flex Start mode, you submit a capacity request for your jobs by indicating how many VMs you need, a duration, and your preferred region. Dynamic Workload Scheduler will queue your capacity request, and once the capacity becomes available, it automatically provisions your VMs for the duration requested. Dynamic Workload Scheduler supports capacity requests for up to 7 days with no minimum duration requirement, and you can even request capacity for as little as a few minutes or a few hours. If your training job finishes early, you can also just terminate the VMs to free up the resources and just pay for what you actually consumed. With Calendar mode, you'll be able to request GPU capacity in fixed duration capacity blocks. It currently supports future reservations with durations of 7 to 14 days, and they can be purchased up to 8 weeks in advance. Your reservation will get confirmed based on availability, and the capacity will be delivered to your project by your requested start date. Your VMs will be able to consume this reserved capacity block, and at the end of the defined duration, the VMs will be terminated and the reservations will get deleted. The flexibility that dynamic workload scheduling provides was a, quote, game changer in procuring sufficient GPU capacity for Linum AI, and we encourage you all to consider enabling it for your Google Cloud environments. So I'm sure the Hypercompute cluster sounds great and that now you're eager to learn how you can use it for your own HPC and AI workloads. Well, that's where Cluster Toolkit comes in. And to tell us a little more about it, I'm going to turn it over to Sam.
Hi, folks. My name is Sam Skillman, and I'm a software engineer at Google Cloud. Over the next few slides, I'm going to introduce Cluster Toolkit, which is an open source tool that can be used to easily deploy HPC and AI infrastructure. I'll then walk through a few examples that are geared specifically towards deploying AI ML and HPC workloads. HPC and AI use a vast range of cloud services and are often customized for each individual's or organization's use cases. These services span compute, networking, storage, operations, schedulers, and runtimes. Combining these systems can often pose a challenge. The Cluster Toolkit was designed to offer a modular solution to this challenge by making it easy to combine each of these pieces into a custom HPC and AI environment. The Cluster Toolkit is a modular, composable toolkit written in Terraform, designed to make it easy to deploy repeatable turnkey HPC AI environments with Google Cloud's best practices built in. The toolkit consists of three key components. First is a blueprint, which is exactly what it sounds like. A blueprint or a design that your HPC AI environment should be built to follow. These blueprints can be specific to a workload, general purpose, or focused on a partner solution. The toolkit is provided with several example blueprints, and users customize them or build them entirely anew to meet their needs. These blueprints reference modules that the toolkit supports, and these modules break down into several types like scheduler and storage. These modules deploy onto our cloud infrastructure we just talked about and run your HPC AI workloads. Let's take a look at how these pieces come together and how the toolkit works to deploy your environment. So, the Cluster Toolkit starts with a simple text file written in YAML format. For a standard Slurm-based cluster, this is only about 60 lines of code to configure all of the compute, networking, storage, and workload orchestration that you'd need. Those 60 or so lines get augmented by all of the GCP best practices and are used to generate thousands of lines of Terraform, Ansible, and Packer configurations that enable us to manage our infrastructure as code. Here's a basic example of a Slurm cluster in a little bit more detail. At the top left, you'll see variables that can be used throughout the rest of the blueprint. These are the only things that you need to edit based on your preferences, things like what location you want to set this up in. First, we set up a VPC, Virtual Private Cloud Network, that will be used for this deployment. Following the best practices, we use separate VPCs for different blueprints. Then we add a Cloud File Store NFS home file system. Note that it uses the network one that we just created. Then we add debug and compute Slurm node sets. These are both auto-scaling node sets so that when your job spins up or is complete and the queue is empty, these nodes will spin back down. We then define debug and compute Slurm partitions, which can be made of one or more Slurm node sets. Here we set the debug partition to be the default, and we use the node sets that we defined previously. Almost done. We then add a Slurm login node, which here we're going to give a public IP address. They can also be a private IP addresses, and you can use IAP SSH tunneling through gcloud to reach the login nodes without a public address. Finally, we define a Slurm controller, which uses the network partitions, login nodes, and home file systems. At the end, you've got a fully functioning auto-scaling Slurm cluster. That was just a basic blueprint example. There are many such examples in the Cluster Toolkit blueprint catalog, which you can find the link to below. And these can be filtered by storage, software and application, machine types, operating systems, and it's a great place to start when you're customizing your own environment. Now we're going to hop into some more advanced toolkit blueprint examples. This first blueprint showcases our recently announced A3 Ultra VMs, which have 8 NVIDIA Hopper 200 GPUs, 2 4th generation Intel Xeon CPUs, 3200 gigabits a second of RDMA networking, and 12 terabytes of local SSD storage. Here we base off of the Ubuntu or Rocky Linux, and this example uses Slurm combined with the automatic installation and configuration of Pixies and Enroute that allow you to easily run containerized workloads. VMs that are here are compactly placed using the extended reservations from the Hypercompute Cluster capabilities that Wyatt talked about. And Slurm has been integrated to automatically schedule jobs topologically. That keeps them compact and minimizes communication time between nodes. Cloud Storage Fuse here is optimized to use local SSD, and File Store here is used for a home file system that exposes NFS. All of that setup for this A3 Ultra Hypercompute cluster on the previous slide allows you to configure and deploy things like NVIDIA's NeMo framework. All that's needed is a few configuration variables such as project ID and cluster size, and the cluster can be deployed with a single command using the gcluster binary from the Cluster Toolkit. You can find much more comprehensive documentation by scanning the QR code in the upper right. Cluster Toolkit is also able to deploy hypercompute clusters based on top of Google Kubernetes engine. We configure the GKE cluster with Q, which is a workload management system on top of Kubernetes. And this enables, again, topology-aware scheduling of jobs. All of the networking and service accounts are configured to adhere to best practices, and local SSD storage here is configured as ephemeral storage for GKE, which speeds up things like large container image load times. Now I'm going to hand it back to Wyatt, and he's going to talk about how you can use Cluster Toolkit for a different type of application, namely CAE workloads. Thanks.
As you saw from the blueprint catalog, we have blueprints not only for AI workloads, but also for traditional HPC workloads like computer-aided engineering. We've worked closely with NVIDIA recently to introduce GPU acceleration to our CAE solution, and you can see the basic architecture that our blueprint deploys here. We have NFS storage, as well as options for parallel file systems, a CPU and a GPU partition, remote desktop instances, and built-in monitoring and logging. This blueprint has also been validated by leading computer-aided engineering application vendors like Ansys, Altair, and Siemens as compatible with their most popular applications. We added GPU acceleration to the CAE solution because GPUs offer the opportunity to significantly improve the performance, fidelity, and ultimately the price of your CAE simulations. Recent benchmarks show that NVIDIA H200 GPUs run some workloads 34 times faster than running on a CPU alone, which makes a tremendous difference if you're waiting hours or days for a simulation to complete. That improved performance can provide better overall price performance as well, allowing you to do more work for every dollar spent. And if you're running faster and saving more money, you might then consider increasing the fidelity or resolution of your simulations to get better results in the same cost and time as before. We've demonstrated those potential performance and price performance improvements that come with GPUs using industry software. For computer-aided engineering, we worked with Siemens to validate the performance of their StarCCM Plus computational fluid dynamics workloads and found that their large parameter vehicle models of over 100 million and 300 million parts performed well on GPUs, and that the optimal VM for those model sizes was actually our G2 VM with NVIDIA L4 GPUs. So not only can GPUs improve the price performance of your workloads, but choosing the right GPU for the job can improve it even further. Now to tell us a little bit about how they've built and optimized their AI infrastructure on Google Cloud, I'll hand it over to Mihir from Contextual.
Thanks, Wyatt. Hi, everyone. My name is Mihir. I'm a member of technical staff here at Contextual AI. Today, I'm really excited to share with you some of the work we're doing at Contextual AI and talk a bit about our relationship with Google Cloud. First of all, what is Contextual AI? Our mission is to change the way the world works through AI. We offer an enterprise AI platform that makes it fast and easy to build production-ready specialized RAG agents. I'm sure most people here are already familiar with what RAG is, but essentially RAG stands for Retrieval Augmented Generation, and it's the de facto way to inject enterprise context into language model generation. What we've done here at Contextual AI is integrate all the necessary components in a RAG system into a single end-to-end optimized platform. This means it's easier to specialize and build RAG agents on our platform, and you'll also get better accuracy out of the box. And since the beginning, we've had a very close partnership and relationship with Google, which has been amazing for us. Much of our tech stack is built on Google infrastructure with NVIDIA GPUs, both for training and for model serving. For example, we're currently using the Cluster Toolkit and Slurm as core pieces of our training architecture. And of course, we'll talk, and of course, all of our work runs through NVIDIA GPUs. I'll dive a bit deeper into the details of our architecture a bit later in the presentation. But first, before going into there, I wanted to share a bit more about our company, how it was founded, and how we operate. One of my favorite sayings is the most powerful is the most personal, and I think that represents Contextual very well. Our founders, Dawa and Aman, worked together for a number of years, initially at FAIR, Facebook AI Research, as well as at Hugging Face. Dawa, our CEO, was a co-inventor and author on the original RAG paper. So the culture of cutting-edge innovation AI research has also been continued here at Contextual. We take a lot of pride in our research. A big part of why we appreciate working with Google is that the infrastructure and compute resources available on Google enable the research team to move very quickly and conduct some really impressive cutting-edge research, which of course ultimately makes our products and services better as well. And in terms of where we focus and what we focus on, earlier I mentioned specialized RAG agents. So let me explain briefly what that means. Almost every company out there has been experimenting with generative AI over the last few years. Understandably, most of them have been focusing on some of the lower hanging fruit that's out there, which are also some of these more general purpose AI tools, which are mostly good for convenience and some general productivity gains. For example, helping with copywriting or being able to ask who your 401k provider is, or also asking how many PTO days you have, are some of those common examples. However, our mission is to help unlock real differentiated value through AI. And the way we're approaching this is to help enterprises address transformational use cases that typically require a lot of enterprise context. These highly specialized and domain-specific use cases at the top of this chart are where differentiated value is found. But they're typically very, very challenging to implement in production. So what we're doing at Contextual AI is we're building a platform that allows enterprises to build specialized RAG agents that focus on these complex domain-specific use cases, such as investment research, product analysis, patent reviews, and more examples like that. So our end-to-end platform enables AI teams to rapidly build and deploy specialized RAG agents, providing state-of-the-art capabilities to accelerate their development cycles and just move faster in general. There are a few core components to the platform. The mouth of the system is basically our data understanding pipeline, which continuously ingests and extracts and processes all of your enterprise data, regardless of the modality, the scale, the size, and of course the format. Our contextual RAG agent retrieves and reasons over all of your enterprise data and is end-to-end optimized to deliver exceptional accuracy and minimal hallucinations out of the box. And then finally, our specialization engine enables you to tune and align your agents to address your domain-specific use cases and achieve even greater performance. So from here, I wanted to switch quickly to a quick recorded demo of our platform to give you a better idea of what our customers are building with us.
Hi there, I'm Dav from Contextual AI. I'm excited to share our platform for building specialized RAG agents with you today. Let me show you some of what it can do. In our UI, you can see some of the agents we've built for a variety of experts, from financial analysts to customer engineers to legal associates. Let's start by exploring an agent designed to help bond investors. Let's say I want to find new muni bond investment opportunities in California. So I'll ask it to give me recent revenue trends for the counties with the highest outstanding debt. You can see the agent's chain of retrieval and reasoning steps. It first identifies the counties with the highest debt principal by querying over a structured database. It then uses that information to retrieve relevant revenue data from PDF reports. The agent generates a response with precise attributions. We can even click into the SQL query that was generated, as well as the retrieved budget documents. Bounding box attributions are included to show where it found relevant information. Let's step into a completely different agent, this time one specialized for hardware engineers. Let's say my team is working on a project using Raspberry Pi modules, and I need to make sure that it meets our requirements. Again, you can see the agent's iterative reasoning. It identifies the best-selling modules from our structured database. It then reasons over the relevant documentation and determines which modules meet our technical specifications. The agent delivers a well-grounded answer that provides the SQL query and the retrieved technical documentation with bounding boxes over the relevant data. Our platform APIs make it easy for you to build your own specialized RAG agents and integrate them into any application. In this example, using the APIs directly, I'm an analyst that needs to collect financial information for a set of stocks. Rather than manually researching each company individually, I can automatically populate a spreadsheet for easy further analysis. This was just a glimpse of what the Contextual AI platform can do. Contact us to learn how to build and deploy your own specialized RAG agent for your use case.
Awesome. I hope they gave a good taste of what the platform is all about. So coming back to how it all works together, Contextual AI is made up of a number of different models and systems across a full pipeline. It's basically an ensemble of these different models and systems. So for example, here for the specialized RAG agents, we're showing some of the main components, like the VLMs and extraction models, the mixture of retrievers, a state-of-the-art re-ranker, as well as a grounded language model. Each of these are a different set of models and systems. So when we look at this all together, we need to consider a few of the different challenges on both the model training as well as the model serving and tuning side. Our team internally at Contextual has built a lot of custom tooling to help with each of these, and being on Google Cloud has been incredibly impactful to help us accelerate these efforts. So taking a look at model training first, there are just a lot of core challenges that we have to overcome to help provide our research teams with the best platform possible. With HPC clusters, we're thinking about how to get the best quality compute resources, best quality networking resources, and we're also thinking about shareable and reliable file systems that can ensure that our researchers can collaborate effectively with each other on different projects and train models effectively. We're also thinking about things like resource allocation with Slurm, and of course, more basic things like observability and visibility into the overall system. Switching gears, when you think about model serving and tuning more, there's a very different set of considerations that come with building and scaling an enterprise platform and productionizing these different model ensembles. A lot of this comes down to on-demand GPU allocation, right? So with hundreds of agents across different time zones and with users across the globe, we have to start thinking about peak demand and load balancing to make sure that we can allocate resources to areas where we really need them. So being able to allocate resources on demand is a really critical functionality, as certain agents may need certain models more at certain times of the day. There are also things like where we actually store these models, right? Things like storing model weights, how we can reduce cold start times when we actually serve and start these models. Also for general infrastructure management, how can we effectively do container orchestration and spin up different services and manage them? How can we, with this complex ensemble system that we have in place, how can we properly track usage across that system? How can we properly isolate failures and errors that might potentially occur in that system? So these are some of the really big questions and challenges that I've been working on solving internally. And looking specifically at model training, when it comes to our HPC cluster, Google has been really, really impactful in helping us solve a lot of these core challenges that I mentioned. The Cluster Toolkit, for example, really helps us declaratively define everything from Slurm to compute and partitions, and everything that we want to have on the storage and observability side. With things like Weka and NFS, we're able to have very, very flexible storage. And with Slurm, we're able to allocate resources very easily to allow our team to collaborate very effectively. I think one of the best things about this is that having the foundation of cluster management being taken care of for us really allows us to focus on more custom tooling and custom requirements that specifically affect contextual. And then on the flip side, when we talk about model serving and model tuning and productionizing these ensemble systems, things like DWS, which is Dynamic Workload Scheduler, have been really impactful for helping us allocate more resources more effectively depending on demand and traffic for specific agents at different times of the day. So we're able to scale up specific models, allocate resources when maybe a tuning job requires it. And then for tooling like GCS, it's been incredible for us from the storage perspective when it comes to storing model weights, loading model weights, and helping us reduce cold start times. And then for observability and tracking activity throughout our system, GCP's managed Prometheus offering and observability offerings have been really, really great and have been giving us incredible visibility into everything we're running. So what are the outputs of this? What are we able to do with the product? Our latest benchmarks are showing that our platform is actually outperforming other RAG systems built with leading AI models like Claude 3.5 Sonnet and GPT-4o. I think one of the things that's most exciting is that not only do we perform better in end-to-end accuracy, but also each individual component of our system, like document understanding, unstructured and structured retrieval, as well as not hallucinating and giving really grounded answers, each component of the system is also state-of-the-art and best-in-class across the entire RAG pipeline. I think one of the really cool things here is that we're the only vendor that is a leader in each of these categories. So we're really the only ones here that are focusing on the end-to-end system here. So these results have been really exciting for us, and our customers are really excited to work with us because of our leading performance. And again, this was all made possible because of all the infrastructure components we talked about earlier through Google Cloud. And one of the great things about Contextual is that we have the opportunity to work with a variety of different leaders and innovators in different industries. Here I wanted to share an example about Qualcomm, who also has a collaboration with Google, where we've been able to build and deploy our RAG agent into their customer engineering team. The customer engineering team is a highly technical team, and they're essentially responsible for solving complex engineering problems for all of their customers. We've built a RAG agent for them that ingests millions of pages of technical documentation and allows thousands of their employees to basically converse with this data and have a conversation to accelerate resolutions of tens of thousands of support cases every single year. It's amazing to see us power critical use cases like this, and we're excited to do even more in the future. So that's a quick look at contextual AI, and it was fun to share some of the exciting work we've been doing over the last little bit of time, and extremely excited to continue working with Google Cloud and the HPC team, and thanks for having us.
Thanks so much for joining us, Mihir. It's great to hear about how you're using Google Cloud for your training and inference workloads, and to see the kind of difference it's making for your customers like Qualcomm. To wrap up, I'd like to share a few places you can find more information about the solutions and Cluster Toolkit guides and blueprints we've discussed during the session. We hope you come away from this session with a better understanding of Google Cloud's HPC and AI solutions, including the range of NVIDIA GPUs that Google Cloud offers, like the A3 Ultra VMs, the benefit that the Hypercompute Cluster brings, the simplicity that the Cluster Toolkit offers everyone looking to run HPC and AI workloads, and how it's making a difference with customers like Contextual AI. We hope to see you at this year's GTC or in our Google Cloud Advanced Computing community, which is a community of practice for professionals working in the domain of advanced computing, including HPC, AI, and quantum computing. We host bi-weekly virtual sessions and in-person meetups, and we hope you'll join us. Thanks so much for your time, and happy computing.